Hello friends, my name is Vikas BSc second year chemistry honors fourth semester. Today we will do the inorganic chemistry chapter. The chapter name is thermodynamics. Firstly, we will do the introduction of this chapter. The first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequence some definitions given to the second law are briefly given below. First point is a major limitations of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process, that is whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to the hot end or not. All that it felt is that if the process occurred, the heat energy gained by one end would be exactly equal to that lost by the other. And similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies answer to the above questions by stating that all spontaneous processes like that flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above the spontaneous process. However, it may be mentioned here that term spontaneous does not give any idea of the rate of the process, that is whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of external agency. Second point is the first law state that when heat is converted into a work, the work obtained is equivalent to that heat absorbed. However, it has been seen from experience that heat absorbed cannot be completely converted into work without leaving some change in the system of the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as follows: the complete conversion of heat into work is impossible without leaving some effect of elsewhere. Besides the above definitions, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are: first is it is impossible to construct a machine functioning in cycle which can convert heat completely into the equivalent amount of work without producing some changes elsewhere. Second point is without the use of external agency, heat cannot by itself pass from a colder to a hotter body. Fourth definition: the term functioning in cycle is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, internal energy is equal to zero, so that heat is equal to work, that is the work done is exactly equal to the heat absorbed by the system. In other words, in this process heat is completely converted into work. However, it is important to observe that this conversion is accompanied by an increase in volume of the gas, so that the system has undergone a change. A number of other definitions has also been given to the second law of thermodynamics. We will come across in the succeed sections of this chapter. The fractions of the heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machines is given by eta is equal to work done divided by heat. The machine used for the conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from a heat reservoir at a high temperature cold, the source converts a part of heat into work and returns the remainder to the heat reverser at a lower temperature called the sink. Second point is Carnot cycle and its efficiency. In order in order to calculate the efficiency of any heat engine, Sadi Carnot derived a technique called a Carnot cycle. A cycle is passed in which a system returns to a original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot for the process purpose of the calculation of the efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylindrical containing 1 mole of an ideal gas as working substance and fitted with a weightless frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reverses, one at the higher temperature T2 and the other at the lower temperature T1. If some operations is carried out by the placing the cylinder in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on a insulating material, no heat exchange can be take place between the system and the surrounding and hence the process is adiabatic. The Carnot cycle consists of 4 different operations which can be represented on a pressure volume diagram. These operations are carried out as shown and are briefly described below. First point is isothermal expansion. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done W1 by 1 mole of the ideal gas will given by. Further, for an ideal gas, the work done is equal to the heat absorbed Q2. Second point is adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown by the adiabatic curve BC. The work done W2 will be given by the where Cv is the heat capacity of the ideal gas. Our here again W2 is negative by the usual convention of sink. Third point is isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink. The gas is compressed isothermally and is reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken by as positive by the usual convention of sign and hence will be given by. During the operation, the amount of heat Q1 exactly equal to V3 will be returned to the sink T1 and that is heat has been given out by the system using The appropriate convention of sign Q1 will be negative and W3 will be positive. Fourth point is adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state. Regained the temperature of the gas rises from T1 to T2. The work done is positive by the convention of a sign and will given by. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been complete. The net work done by the system will given by Carnot theorem. From equation 13, it is clear that the efficiency of the reversible heat engine depends upon the temperature of the source and sink and is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operations, because the work done is adiabatic operations cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion is a maximum, whereas the work done on the gas during the reversible isothermal compression is minimum. Hence, the total work done by the system is maximum for the specified condition, and therefore the efficiency is maximum. The result that follows from the Carnot cycle is called Carnot theorem. It may be stated that as follows: the efficiency of a reversible heat engine depend only upon the temperature of the source and the sink, and it is depend on the nature of the working substance. In the other words, all reversible heat engines working between the same two temperature have the same efficiency. Further, it said that the efficiency of a reversible heat engine is maximum for the given temperature. Since the quantity T2 minus T1 divided by T2 is always less than unity, the efficiency of the heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined below as: a heat engine absorbs a certain amount of heat from the source, converts a part of it into work, and returns the rest of the sink. In other words, it is impossible to convert heat completely into work. The result derived for a reversible Carnot cycle leads to the introduction of a new thermodynamic term called entropy. Second topic is thermodynamic scale of temperature. From our earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of capillary tube and marking 0 when it is placed in contact with the ice and marking 100 when it is placed in the boiling water. The length between the 2 points is then divided into 100 equal parts called degrees. The scale of temperature thus obtained is called a Celsius scale of temperature. However, because different liquids expand to different extents, that is their coefficients of expansion of different, and also they do not expand uniformly over a given range. Thermometer constructed by using different liquids will show different numerical values of temperature between their fixed points. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer, but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by study of properties of gases. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale, and it is found that to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of this temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale, and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken in the heat engine. This scale of temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly described below. Suppose there are two constant temperature heat reverser, one acting as a source and other as a sink, and a reversible heat engine operates between them. The temperature of each reverser on the new scale may be taken as proportional to the quantity of heat absorbed from the source, and the heat lost to the sink may be taken as proportional to the quantity of heat absorbed from the source, and the heat lost to the sink. Then if their temperature on the thermodynamic or Kelvin scale are represented by Q2 and Q1 respectively, we shall have thus this ratio of two temperature has been defined in a manner independent of the nature of the thermodynamic substance. This implies that the zero on the Kelvin scale is the temperature of the sink for a reversible heat engine whose efficiency is unity, that is which is capable of converting heat completely into work. But from equation 14 page 86 it is maybe seen that it is possible only at absolute zero on the ideal gas scale temperature. This leads to the conclusion that the Kelvin scale and gas scale are identical provided the gas is heated. The temperature on the thermodynamic scale are therefore expressed in terms of degrees Kelvin. Further, it has been found that if the lower fixed temperature is taken equal to the of triple point of water, then Kelvin is exactly equal to Celsius degree. For this reason, the temperature on this absolute scale in which the melting point of ice taken as 273.16 degrees is often referred to as degrees Kelvin. It may be concluded that thermodynamic scale of temperature as defined on the basis of second law of thermodynamics is more basic than that of based on the ideal gas, because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of entropy as a state function. For a reversible Carnot cycle working between temperature T1 and T2 has been seen that where Q2 is that heat absorbed isothermally and reversibly at temperature T2, and Q1 is the heat lost isothermally and reversible at temperature T1. Thus, we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost in the constant quantity of a particular system. Further, in equation 2, Q2 is the heated absorbed at the temperature T2 and Q1 is heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, equation 2 would be written as now consider any reversible cycle ABA. It may be regarded as being made up of a number of Carnot cycles drawn across the diagram as shown below. So starting from A and going through all the cycles successively from A to B, it can be shown that all paths inside the closed curve ABA cancel each other, leaving only the zigzag path, which is almost the same as the path ABA of the reversible cycle. By making each Carnot cycle smaller and increasing their numbers, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of an infinite number of Carnot cycles. For each of these cycles we have hence for an infinite number of Carnot cycles where delta Q is a very small quantity of this heat absorbed at temperature T during the small isothermal change of this reversible. Further, the above term may be divided into two parts, one for the path A and to B and the other for the back path B to A. This implies that the total volume of the quantity Q by T for the path A to B is equal to the total value of the quantity Q by T for the reverse path B to A. Hence, it may be concluded that quantity Q by T is a state function, that is, its value depends only upon the initial state A and the final state B and is independent of the path. Obviously, Q by T is the change in the value of the quantity or a function having some definite values at A and B depending upon the values of pressure, volume and temperature. This quantity or the function is called entropy and usually represented by the symbol S. Thus, if SA is the value of the entropy at A and SB is the value of the at B, that we can have, whereas delta S represents the total change in entropy is going from the initial state A to the final state B. Hence, the entropy may be defined as the state function, the change in the value of which from the initial state to the final state is equal to the quantity Q by T, that is the total heat absorbed reversibly and isothermally is going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. From the equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature at which the heat is absorbed. It is important to note that an entropy is a state function. Therefore, the value of entropy change during a process should not depend upon the path, that is, whether the heat is absorbed reversibly or irreversibly during this process. However, since the derivation of the above result is based upon the Carnot cycle in which the heat is absorbed reversibly, therefore the expression of equation 6 for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use symbol Q reversibly in place of Q. The expansion of equation 6 may be therefore written as further: an entropy is a state function. A small change in its value can be represented by ds, hence we can maybe write. So our chapter is complete.